Hey Nick,
Hey Guy. Hey Vincent. Thanks for coming early.
sure. Yeah, nice
Hey,
to meet you virtually.
Okay, Guy, could you try sharing your screen
Yes.
to make sure it works? Andrew.
1 second. Yeah, this one. Can you see it now?
Yeah, can you try going full screen? Perfect.
Great.
Okay, and then Vince, can you do the same?
yep. Does that work?
Yeah, that looks good.
Cool.
Okay. Hi, Yen-Ting.
Hi.
I have your recording and I think I'm just gonna play it.
Perfect. Yeah.
Okay. This is like the first time everyone's shown up on time.
Had to be extra on top of it because Monday, 9 a.m. for the Pacific time. I was like,
Yeah.
better get to the office a little early, make sure I don't slip up. Monday, 9 a.m., normally just kind of being a little sluggish to get the week started.
Yeah.
Yeah. I'm curious what that meant for the attendance because the Monday morning usually people are not in the mood for work but also don't have any schedule. So it can go either way.
Totally.
So I think Andrew emailed you. We're gonna go in kind of reverse order of current time. So it'll be Yenting, then Guy, and then Vince.
Sounds great.
Thank you.
Yeah, sorry, Vince, but you've got a whole day ahead of you, you know.
Yeah,
Relax.
I made a video because it's hard to commit how my background noise would
Yeah.
be if my kids wake up. So I feel more at peace this way, so I can go anytime if I have to.
Smart.
Hey, Jonah,
Hi,
you made it.
Jonah.
Hey, Jonah.
Hi everyone. Good to see you.
Hi.
Hey.
Thanks so much everyone for doing this.
Yeah, thanks for organizing.
Yeah, thank you.
Oh.
Is anybody in the UK? What time is it over there? No?
I believe Jonah
It's
is.
almost 5 p.m., but I'm actually in the States right now. So maybe
Okay.
someone will be there eventually.
Andrew, you're in Princeton now?
Yeah, I live in New York, but I'm
Oh,
at like yeah, I'm starting the Princeton job, yeah. Um
which part of the city are you in?
Inwood, like Upper Manhattan.
Oh, wow.
Yeah.
Jonah's from
Uh,
Manhattan.
Jonas suggested Inwood
Yeah.
as a place to live. So
My folks
good.
lived there for just like a year, and I thought it was a wonderful neighborhood. So I'm
Nice.
glad you're there.
Yeah. You didn't lead me astray. It's pretty good. Pretty good.
Mhm.
I would have had someone to blame if it was bad though.
That's right. That's right.
How long is the commute to Princeton from there, or do you mostly work from home?
It's like 2 hours. So I'm currently like super commuting. So I go in on Tuesday morning and then come back Thursday night and like
Okay.
couch surf in
Yeah.
between. Um, but but this week I've got stuff on in New York, so I'm just gonna work fully remotely for a week. Um, yeah.
One of our fellow grad students, Adam Sokol, if you've seen him around, he's currently scouting out the same situation of trying to maybe do like Princeton, his girlfriend's at Yale, maybe being in New York, like trying to figure out how long it would actually take to get around between all these places that seem so close as the crow flies, but often it actually takes kind of a long time to get around.
Yeah, we actually had a similar situation because my partner was applying for grad school and well, what Yale was like one of the places that she was quite
Yeah.
keen on. So we were also doing the same type of calculus about whether you can
Piece it
It
together.
yeah, exactly. It just about works out.
Mhm.
If I look dazed and confused at any point, it's because my cat is being really crazy under the table and just scratching at my feet. So if I suddenly run away, that's why. Yeah.
Can we see this cat?
And well, now she's
Excellent, excellent. Now, of course, once the camera's on the cat, then it calms down and acts like everything's normal and chill.
Yeah,
And then
exactly.
as soon as the camera's off, then
yeah, it's the perfect crime.
Can definitely be a good accessory while you're giving the talk if you can manage to have like the cat do a little cameo across the screen. That's something that I know Kyle has managed in a few talks. He'll be giving a talk from like his couch or something, and the cat kind of pops in there.
Prime time, it's the cat goes across just as people's attention's starting to dip, and then yeah. It's very well trained, I'm sure.
Bring people back into focus.
Mhm.
Yeah, give it a few more minutes. People are starting to show up. All right, I'll just get started. So thanks everyone for coming to the 28th ECS and Cloud Feedback virtual symposium. A few notes before we get started. So if you haven't come to these before, we'll have 3 AGU style talks. So somewhere between 12 and 15 minutes with some time for questions. And then if there's time, we'll have a short general Q&A after the last talk. If you have questions or comments, type them into the chat at any time or raise your hand and we'll ask you to unmute yourself at the end of the talks. The comments tend to be pretty lively, so keep an eye on them. Yeah. And please get in touch if you'd like to give a talk at a future event. And we're also still looking for one new executive committee member to replace our founders, Andy and Christy, or the emeritus founders. But otherwise, email Shia, Jonah. Actually, Andrew's not on this yet, or Andrew Williams, who just joined the executive committee. And our contacts, recordings of past talks, mailing list sign up, and more are at the Google site where we host everything. Okay. So with that, we'll go to the first talk, which is a recording by Yen-Ting Hwang. Yen-Ting is an associate professor at the National Taiwan University, and she pre-recorded her talk, but she'll also be here to take questions at the end. So I'm going to start it. Can everyone hear this?
Hello, everyone. It's Ting speaking here. I would like to start by acknowledging my students and collaborators listed on this slide. This is a team effort. They make the work I'm about to present possible. The key results are described in Boru Chen's master's thesis, and our manuscript is just submitted, which applies the magnistics understanding that's built upon Zheng Hongyi's PhD thesis and Wei-Ting Xiao's bachelor thesis, which are both published. Since this is the ECS Symposium, I borrowed this climate sensitivity plot from Kyle Armour to motivate our work. This plot illustrates the community's effort in reconciling the discrepancy between the lower climate sensitivity estimated from observational data and the higher climate sensitivity reported by global climate models. The disagreement can be explained by the observational method. Differences in forcing agencies, as they observe records, are affected by forcing other than CO2, and the climate sensitivity estimated from a shorter time record may be lower than that in long-term equilibrium, and the time dependence can be attributed to the time-evolving sea surface temperature pattern showing in this slide. The story I'm going to share today is related to the last two modifications. Previous studies that demonstrate the critical role of anthropogenic aerosols' influence on cooling the equatorial Pacific all suggest that the influence will fade out as the emission continues to decline. So my question for you is when? When do you think that will happen? We suggest that, like CO2, we should consider both the fast and the slow components when thinking about the tropical sea surface pattern responses to aerosol forcing. The plot on the left shows the fast response of aerosol recovery that I'm going to introduce in this talk. Note that I demonstrate the absolute values of the linear trends here. While the northern hemisphere warms up rapidly, the Southeast Pacific actually cools, similar to the observational trend on the right. Whereas the 4x CO2 plot that I've just shown in previous slide, that showed the related SST, and the equatorial region actually warmed, but just warmed less. I'm hoping to make a case that in order to understand anthropogenic aerosols' contribution to the historical sea surface temperature pattern or near future projections, we need to take into account the complex response timescale of tropical Pacific sea surface temperature. Let's start with a realistic scenario, the CSM1 single forcing large ensemble. Do you expect the NINO 3.4 index to recover as the aerosol emission and the associated radial forcing reduces? So you can see from this plot that it started to reduce from the 80s. When do you think the NINO 3.4 index will recover? I'll insert an awkward silence here in the video for you to sketch the answer. Ready? Ta-da! There's almost no sign of a reversal of the cooling trend at the beginning of the 21st century. If we dive deeper to the equatorial subsurface, we are right about to enter the maximum of aerosol-induced cooling. So how do we understand this? Similar to 4 times CO2, we could impose a step function aerosol forcing, which contains a realistic emission distribution as in the 1980s condition. We impose them abruptly and keep them there for 30 years. After that, we return the emission to pre-industrial condition to see the fast and slow components for aerosol emission and reduction. And we run 30 ensemble members to see the clear force response pattern. And you are now seeing the result from this idealized step function type aerosol forcing experiment. The multiple response time scale is apparent when you look at the entire evolution. The equatorial region warms before it cools. After the aerosol reduction takes place, the cooling enhances before it diminishes. We also see the delay cooling in the subsurface. The evolution of the vertical structure is fascinating. The cooling continues to grow for a decade after the aerosol reduction takes place. So in the rest of my talk, I'll walk you through the formation mechanisms for the fast and slow components, which are defined as anomalies at these different stages in the idealized experiment. Here you are looking at the cross-section of the equatorial region and see the evolution. So let's first look at the fast response for aerosol emission. To orient ourselves, let's start with the cooling in mid-latitudes. Anthropogenic aerosols, which are mainly emitted from the industrial area concentrated in northern hemisphere, reflect sunlight. Together with their cloud indirect effects, adding aerosol into the system abruptly cools the mid-latitude in almost all longitudes. The response in the tropical Pacific, however, has the opposite sign from the imposed cooling. The structure looks very similar to those observed in 4 times CO2 experiment, the so-called dynamical thermostat pattern, with the opposite sign. The triggering mechanism is different though. The dynamical thermostat mechanism focusing on the local radiated effects and the delay warming in the equatorial eastern Pacific. When we apply emission from the tropics aerosol only, so we only impose emission in the tropics in this idealized experiment, we do not see the warming pattern, supporting the notion that the chain of air-sea interaction in the equatorial tropical Pacific is caused by the emission from north and tropics and is triggered by the anomalous northerly wind in the East Pacific showing in this pattern. And here's the fast response for aerosol reduction, which shows a very similar pattern with the opposite sign. The pattern formation mechanisms we obtained from the idealized band-like extratropical forcing experiments work perfectly to explain the fast component of aerosol emission and recovery. By comparing the response pattern in the slab ocean model in the right with the fully coupled models on the left, we came to a conclusion that the air-sea fluxes hold the keys for forming the pattern, and ocean dynamics enhances the signal in the central equatorial Pacific slightly. The air-sea fluxes that shape the pattern are driven by the cross-equatorial helices shown on the left in the schematic. Responding to the heating in northern hemisphere, you can think of it as the effect of aerosol recovery that's imposing heating in our system. The cross-equatorial helice develops and transports energy from the north to the south through its upper branch. The lower branch enhances the tray in the southern tropics and reduces the tray in the northern tropics. Increasing wind speed in the southern tropics leads to more evaporation, a cooler SST, and the opposite effect of clouds in the east and in the west. In the eastern Pacific, in the low clouds region, the cooling increases boundary layer stability, leading to more low clouds, more sunlight reflection, and a positive feedback for the initial cooling induced by evaporation. In the west, however, the cooling inhibits convection, resulting in less clouds and a negative feedback. The east-west gradient induces by clouds that further affect wind and evaporation. Clouds appear to play a critical role in shaping this wedge-shaped pattern, which has been demonstrated in the cloud locking experiment in our GL paper listed here in this slide. So after describing the fast pattern that's essentially driven by the cross-equatorial helical, we now turn our attention to the slow response. I would like to highlight that the slow response happens rather quickly. The warming of the fast response disappeared and is replaced by the cooling centering at the equator in year 4 or so in our idealized step function experiment. This timescale appears to be much shorter than what one would expect from the oceanitudinal mechanism, the ventilation, namely T prime V bar. So many global warming and previous epidemic literature highlights the role of climatological subtropical cell that transport the anomalous temperature from the extratropics to the equatorial region. We do see the effects of climatological adaptation in our experiment, as shown in this slide. However, you can see that the anomalous temperature kind of stopped at 20 degrees or so. When performing the equatorial Pacific energy budget, we find that the V prime T bar term explains all of the cooling. The strengthening of the northern subtropical cell, which is induced by anomalous wind and temperature, acts to transport more energy away from the equatorial region and drives the cooling of the slow response. Matt Longo, who gave a talk in this ECS-Symposium, has a very nice paper demonstrating the key role of anomalous temperature or anomalous density in driving the strengthening of the northern subtropical cell. And I think the density-driven component explains the long-lasting cooling in the equatorial region, in the subsurface, actually. In this slide, you can see the anomalous cross-equatorial helicell that disappear within a year after switching off aerosol at year 30, whereas the strengthening of the northern subtropical cell persists for a decade. After the aerosol emission is returned to the pre-industrial condition in this idealized experiment, the cooling induced by aerosol indirect effect or the air-sea fluxes that's driven by the fast response remain. So you can interpret our result as the rapid helicell adjustment set the stage for the slow response of STC, the subtropical cell, which continues to cool the equatorial Pacific, even the cross-equatorial helicell is no longer there. So that's all I wanted to share. I hope I make the case that in order to understand the tropical Pacific SST pattern response to the increase and the decrease of aerosol emission time series, you need to consider both the fast and the slow component. So for the observational record, say 1979 until now, you need to consider the fast response of aerosol recovery that induce warming in the north but cool in the south, that start from the Southeast Pacific and extend to the equatorial Central Pacific. Meanwhile, the cooling that was originally induced by aerosol emission in the 80s persist and continue to drive this northern subtropical cell, which lead to this cooling in the equatorial region that you can see not only in the aerosol-only forcing experiment, but also the O-forcing experiment, the subsurface in the equatorial region actually cool despite the imposed CO2 forcing in those experiments. So that's all I have to share, and thank you for listening. I'm actually online so I can take questions.
Awesome, that was fantastic. Thanks, Yen-Ting. Do you want me to leave the presentation up so you can refer to
Either way, I can share a screen if there are questions
Okay,
too.
I think I might stop sharing.
That was easy.
Easier for me.
It's good to give a talk without talking. So do I answer questions now or do we wait?
Yeah,
Yeah.
I think there's a question from Kyle here. So it says, I wonder if this helps us understand why I wonder if this helps us understand why models can't capture the observed Eastern Pacific cooling since 1980. They have aerosol forcing after all. Do they have the wrong forcing magnitude, pattern, or time series, or other model biases?
Yes. Thanks for the question. I do think there are thoughts, there are like associated with these fast and slow components, one can then decompose the biases. So ideally, we can then have a mechanistic understanding of the where the bias is coming from. So take the fast response, for example. I imagine the double ITCZ bias would affect how the Southeast Pacific affect the equatorial Pacific if the model tend to have a to southward of the ITCZ that will block the signal. And also the long-standing cloud biases that has been highlighted in Southern Ocean telecom action, the work that Sarah and her student did, Hanjin. I think that will also play a role in our telecom action in the other way with the north minus influencing the south. And for the slow components that has to do with STC, which I know less about, but I imagine there's a way to deal with that too.
Great. And then we've got another question from Deirdre saying, any thoughts on the persistent cold PDO? So I guess
that seems to be a big question.
Yeah. Link to
Well,
Kyle's question.
I think if we only look at a North Pacific, so the traditional definition of PDO, then one would think that the reversal have already taken place around like 2015 or so. So back in like 10 years ago, when people look at global warming hiatus, we thought that was PDO, so it was natural. But now 10 years or more than 10 years after, the cooling persists. And if you look at actually, I might have a plot to show, but I may not grab it quick enough. One can compare the trend between, I'll try to send one later, but one can compare the trend between 1979 to 2014 or 1979 up until now. Then you can see that the latter one is more north-south asymmetry. So I think while the PDO kind of diminishes, the Southeast Pacific cooling persists, and so does the equatorial cooling. I don't know if that answered the question directly, but yeah.
And there's a question from UA as well, which says, great talk. Does the mechanism opposite change in the tropical SSTs between the fast and the slow response also work for other thermal forcings or for aerosol in the Southern Hemisphere?
Yes and no. So we have these idealized eta-MIP type forcing that allow us to look at mechanism in either the north or the south. So vaguely speaking, they work similarly, but in terms of the exact pattern and time scale, it isn't. For example, the northern hemisphere is very good at affecting the south. So whenever you warm or cool the north, then Southeast Pacific really affect the south. Whereas when you put the forcing in the south, it seems that there are competing mechanisms to affect the east-west gradient. So there are climatological advection, and then some signal go through the Indian Ocean. Whereas in the north, you always have this PMM-like pathway that would then change the east-west gradient along the equatorial region. So I think big picture speaking, if you look at zonal mean, like if the equatorial warm or cools, then yes, the two work similarly. But if you look at the detailed structure of zonal structure, then forcing in different hemisphere aren't identical.
Cool. And yeah, Carsten says that his question was very much like UA's, so we should probably move on. But Thanks, Ting. And I guess you'll hang around for a little bit in the chat. If people have more questions, they can just put them in there.
Thank you. Sounds good.
And thanks, Yen-Ting. So we're gonna move like 8 or 9 time zones west, and Guy Dagan is gonna present. Guy's a senior lecturer at the Hebrew University of Jerusalem. And take it away.
Thank you. Yeah, so I'm going to talk about aerosol-cloud interaction in the climate feedback forcing framework. And I'll try to briefly mention 2 points or 2 papers, basically. The first one focused more on the forcing side of things and present results from a paper that should be out soon, done together with my student Neta Yechezkel and with Andrew Williams. And in this paper, we are showing that the effective radiative forcing from aerosol-cloud interaction is enhanced by large-scale circulation adjustments. And toward the end, I'll also try to briefly mention another paper in which I showed that aerosol-cloud interaction affect the magnitude of cloud feedback and the equilibrium climate sensitivity. Starting first from the large-scale circulation adjustment. So adjustment refer to changes in the system structure or composition, including large-scale circulation changes that impact the top of atmosphere energy imbalance without changing the SST. And we know that large-scale circulation changes strongly affect the effective radiative forcing from CO2, from greenhouse gases, and from aerosol radiation interactions. But very little is known about large-scale circulation adjustment due to aerosol-cloud interactions. And this is because it's a very challenging question to try to answer. When we study aerosol-cloud interactions, we want to work in fairly high spatial and temporal resolution in order to be able to resolve cloud processes good enough. And we also want to have a detailed representation of the microphysical processes. And that usually dictates that we will work in fairly small, limited area cloud resolving model. And traditionally, in limited area cloud resolving models, one prescribes the boundary conditions. And no matter how we choose to do it, there are a few different ways to do that, but nevertheless, never mind how we do it, once we prescribe the boundary conditions, we basically turn off any interaction between the local scale and the larger scale. So we turn off any interaction between cloud and large scale circulation. And this is obviously a major limitation. So what Abut and Cronin did in order to try to tackle this major limitation is to use a weak temperature gradient approximation in order to have a prognostic large-scale vertical velocity in a limited area cloud resolving model. And by doing that, they enable some kind of representation of the coupling between clouds and the large-scale circulation, and the local aerosol-cloud interaction affect the large-scale vertical velocity. It affects the convergence of water and energy into the domain, and so on. And I think that this is a major step forward that enables us to study this really challenging question. But the issue with this setup, and we showed it in this paper that was published last year, is that it does not conserve water and energy. Basically, there is no limitation on the amount of water and energy that can converge into the domain. And I think that this could inflate the magnitude of the aerosol-cloud interaction. So ideally, we would like to have a setup that enables representation of the coupling between the local ACI and the large-scale circulation, but does it in a way that conserves water and energy. And that's what I tried to do in this paper that was published in James last year. And what I did here is to couple 2 LES domains. One represents the tropical atmosphere, and the other represents subtropical atmosphere. The 2 domains are coupled through a weak temperature gradient approximation in a way that in each domain there is a prognostic large-scale vertical velocity, and the 2 domains affect one another. And the 2 domains also exchange water and energy in a way that represent an idealized overturning circulation, such as the Hadley cell or something like that. But it does it in a way that conserves water and energy in the entire system. And I think again, that this is a step forward because now we can start to ask questions, for example, how a local aerosol cloud interaction perturbation in the subtropics affect the clouds downwind in the deep tropics and so on. But one could argue, I would argue that the representation of the large-scale circulation here is very crude and idealized. Basically, we have a crude parameterization of the large-scale circulation here, and we would like ideally to have both, being able to resolve cloud in high temporal and spatial resolution, and also have resolve large-scale circulation. And that's what we are doing in this paper that is about to be out soon. In this paper, we took a different approach that actually was used quite a bit in the cloud feedback and convective aggregation communities, but wasn't used in the ACI and Aerosol-cloud interactions community. And in this approach, we are using a long and narrow channel-like domain that enable us to work in fairly high temporal and spatial resolution, but still account, at least in one of the horizontal dimensions, for the larger scale. And we are running this geometry either with homogeneous SST conditions, which we'll refer to as RC large, and this is following the RC EMIP protocol, or with an SST gradient along the long dimensions, something like that. And once we have this SST gradient, a large-scale overturning circulation is formed, driven by this SST gradient. And this overturning circulation resembles the Pacific Walker cell, so we'll refer to it as the Mock Walker setup. And over here, you can see snapshots of those, the outgoing long-wave radiation from those two modeling setups. Over here, we can see the manifestation of this formed overturning circulation in the Mock Walker setup. We see here Hofmöller diagrams of the surface precipitation, outgoing long-wave radiation, and top of atmosphere short-wave radiation. And you can see that most of the precipitation and most of the deep clouds are formed at the center of the domain where the SST is warmest. So we get convergence toward the center of the domain and subsidence at the edges where we get mostly shallow clouds. For each SST distribution, either homogeneous or with an SST gradient, 3 different domain means SST were considered. And for each SST, domain mean SST and SST distribution, 3 different levels of aerosol concentration were simulated for a few hundred days each simulation. And over here, we can see the response of the top of atmosphere energy gain in panel A to an aerosol, to an increase in aerosol concentration. The solid lines represent the Mock Walker setup, and the dashed lines represent the RC large setup. And the different colors represent the different domain mean SST. So the most significant thing we see here is that we get a much stronger response in the Mock Walker setup compared to the RCE large. Okay, so the effective radiative forcing of aerosol cloud interactions is much stronger, much larger, negative, but larger when we have in the presence of overturning circulation. And this strong effective radiative forcing is coming from the shortwave part of the spectrum with a weak response in the long wave. And unsurprisingly, it's coming from the cloudy sky, from cloud radiative effect genus. We can explain this strong effective radiative forcing by very strong cloud adjustment. So we see a very strong increase in the liquid water path and in the cloud fraction in the Mock Walker setup, while in the RCE large, we get a much muted or even negative response. So basically, in the Mock Walker setup, when we increase aerosol concentration, we get more clouds that reflect more of the shortwave radiation and leading to a stronger negative effective radiative forcing. And another thing we can see here, and we'll get to it in a minute, is that the surface precipitation, domain mean surface precipitation, increases in the Mock Walker setup while it decreases in the RCE large. Now, in order to better understand those results, I would like now to separate the domain of the Mock Walker setup to 2 different parts. The central part where we have mostly deep convection, where the SST is warmer than the average, and the shallow dominated part where we have mostly subsidence in lower than the average SST. And over here, we see the response of the surface precipitation in the shallow part and in the deep convective part under the different SSTs. And you can see that increase in aerosol concentration suppress precipitation in the shallow dominated part for all different SSTs, while it caused an increase in the amount of precipitation in the deep convective part. Okay, so aerosols suppress warm rain at the where we have shallow clouds, and then with the overturning circulation, we get stronger advection of water vapor from the shallow to the deep part, and that's what we see here, stronger advection of water vapor with the overturning circulation into the deep tropics. We get stronger convergence of water vapor into the deep tropics that result in more precipitation there, more latent heating, which generates stronger advection of dry static energy from the deep convective region into the shallow region. So basically, we see here that increasing the aerosol concentration intensify the strength of the overturning circulation. And in the paper, we're also showing it more directly using near surface wind speed and large-scale vertical velocity at the middle of the troposphere. So to sum up this part, in the presence of an overturning circulation, when we increase aerosol concentration, we suppress rain from shallow convective clouds in the regions of the lower SSTs. That causes stronger advection of water vapor from the shallow region into the deep convective region, stronger convergence of water vapor into the deep convective region, more precipitation there, hence more latent heating, which intensify the strength of the overturning circulation. And stronger overturning circulation is also accompanied by stronger near surface wind speed, which cause more evaporation. And this acts as a positive feedback because it further enhances the advection of water vapor into the deep tropics and causing more conversion of water vapor into the deep tropics and so on. In addition, the increase in surface evaporation increased the cloudiness in the shallow region, which reflect more shortwave radiation and leading to a stronger effective radiative force. Now, I won't go into too much details, but in the paper we conducted, we are presenting a mechanism denial experiment in order to quantify the role of this positive feedback that I just mentioned, this WISHI, wind-induced heat exchange feedback. And we are doing it by prescribing the near surface wind speed for the calculation of the surface fluxes only. And we are showing that this positive feedback accounts for about 1/3 of the effective radiative forcing. We also presenting an ensemble of transient simulations which demonstrate that it is indeed the intensification of the near surface wind speed that lead to the positive cloud adjustment, which in turn lead to the strong effective radiative forcing. It also demonstrates that it takes about 30 days for the large-scale circulation adjustment to establish, which justify the using of the fixed temperature, fixed SST assumption. Now, I want to briefly mention the other paper. It will only take me about 30 seconds. In this paper, I show that the equilibrium climate sensitivity increases with aerosol concentration in RC simulations with a slab ocean model. And this is causing due to changes in the precipitation efficiency. So Nick and others showed before that the precipitation efficiency increases with warming. But here I'm showing that the rate of increase is faster for higher aerosol concentration. That leads to less negative cloud feedback and hence higher equilibrium climate sensitivity. And I want to mention it because I think that it is important to remember that aerosol-cloud interaction and cloud feedback are not separate things, and we should study them together. And currently, together with Philip Stier and Suvan Den Hever, we are organizing an RC-EMIP stage that will be focused on ACI. And the idea is to study how cloud feedback, equilibrium climate sensitivity, convective aggregation, and so on are affected by aerosol-cloud interactions. The simulations are starting to accumulate, but if you want to contribute simulation to that, you can still join. If you want to use the data or have any questions about it or so on, please get in touch. Thank you very much.
Great, thanks, Guy. Great talk. We have a couple of questions that have come in already. So one's from Jonah. It says, great talk. Any idea why the 305 Kelvin Mach Walker simulation has a stronger response to aerosols than the colder ones? So yeah, thanks for this question. I think that when you look at it in relative magnitude, actually it doesn't, the cloud adjustment there are not stronger. So if I go back to this figure, oops, sorry. So yeah, you can see that in absolute magnitude, the cloud adjustment here are stronger, but in relative magnitude compared to the baseline, they are not so much stronger. We just have more clouds, there are more liquid water path and higher cloud fraction there to begin with. So I think basically that the relative response is the same, roughly. Cool, great. And then there's another question from Rob Wood, which says, are you able to qualitatively reproduce the Mach Walker results using the simple weak temperature gradient parameterization from the two-domain LAS? Are they consistent?
Yes, so we are getting qualitatively similar results. So I didn't show here, but we also did in the Mach Walker setup simulations where we only perturb the shallow convective region, or only increase the aerosol in the deep convective regions. And we are saying that the aerosol in the subtropical or the shallow convective region are more important to the increase in the circulation. And the same was shown in the coupled two-domain setup, where I showed basically that when we increase the aerosol concentration in the subtropics, that enhance the advection of water from the shallow to the deep part and enhance the advection of dry static energy in the opposite direction.
Great. He says the agreement seems encouraging, which I think it does. Cool. Thanks, Guy. I think if you have any more questions, put them in the chat and Guy will hang around for a bit to pick up on those. Thanks again.
Thanks.
Yeah, thanks, Guy. Really thought-provoking set of results. Our last speaker is Vince Cooper, who's a grad student at the University of Washington.
All right. Thanks, Nick. So I'm going to be sharing some work today on the pattern effect at the last glacial maximum. And I'm focusing on global energy budget constraints on ECS. So these were a focus of the Sherwood et al. 2020 climate sensitivity assessment. And as a reminder, you can see in this plot of climate sensitivity from the historical record on the right here, that when we account for the pattern effect, the recent historical record doesn't really constrain the upper bound on ECS at all. And the reason for that is the SST anomalies over the recent historical record are systematically different from the equilibrium anomalies that we expect from CO2 forcing. So in the long term, we expect more positive feedbacks from amplified warming in the Southern Ocean and in the East Pacific. But the paleoclimate periods were also a main source of evidence in this Sherwood et al. 2020 assessment. And the LGM, or the last glacial maximum, actually provided the strongest constraint on the upper bound for ECS. But what we've been wondering is whether there might be a pattern effect also in that LGM evidence that has not yet been accounted for. So I know the physics of the pattern effect have been explained plenty of times here already, so I won't go into too much detail, but I'll just briefly review that the global mean radiative response to a local SST anomaly depends on the location of that anomaly. So if we have SST changes that occur in these kind of blue regions of ascent or deep convection, that's going to tilt the scales toward more negative overall feedbacks. Whereas if we have SST changes that are in the red regions of overall descent, that will tilt the scales toward more positive feedbacks. One thing that's important to remember, though, is that it's not just the East versus the West Pacific that matters. If we have SST changes that are amplified outside of the tropics, so outside of the blue regions, that will just generally tilt the scales toward a less negative overall feedback and also give a higher climate sensitivity. So we can keep that in mind as we start to think about the LGM. Now, if we look at the spatial patterns of forcing, you can see that the CO2 forcing, as expected, is relatively uniform, but the forcing at the last glacial maximum is much more localized at higher latitudes. So the LGM is around 21,000 years ago. This is a recent, or the most recent, major cold period. We had the Laurentide ice sheet covering much of North America, and that represents the largest component of the forcing at the LGM. So we have ice sheets as the major source of forcing, followed by CO2, and then other forcings. And an important point with these plots is that we're looking at the effective radiative forcing here. So that means that the rapid atmospheric adjustments are already included in this forcing figure, but the surface temperatures haven't changed. So the surface temperatures are held fixed. For the rest of the talk, I'm not actually going to talk about the forcings themselves, but rather focus on the response to the forcings. So I'm going to be talking about the feedbacks and the changes in surface temperature that follow. Now we can compare the SST patterns from near equilibrium CO2 forcing from long run MIP. So these are simulations that are more than 1,000 years. We can compare those to a reconstruction of the last glacial maximum, which is on the right here. And if you inspect the SST patterns, one thing that jumps out is there's a major difference in the SST pattern, especially in the northern extratropics. So this is right where we expect a major atmospheric stationary wave response to the presence of the Laurentide ice sheet, so both kind of upstream in the Pacific and downstream in the North Atlantic region. And these SST patterns will project differently onto the Green's functions that represent, or at least provide intuition for the radiative responses from those SST patterns. So because the SST patterns project differently on the Green's functions, we could at least expect that these different patterns might produce different feedbacks. One major advance for this work is the data assimilation piece here. So the patterns on the right aren't just coming from coupled model simulations. We're also able to now bring in observational constraints to provide fully gridded estimates of what the LGM looked like. So I'll give a quick one-slide overview of data simulations. It's an important piece of this work. And everything you really need to know is just in the simple Kalman filter equation at the top here. I'll walk through the components. So we start off with a prior estimate of the state that comes from an ensemble of climate model simulations. And then we compute the difference between proxy data and the estimate of that proxy data that comes from the model prior. Once we have that difference, we can use this K term, which is the Kalman gain. And what that does is it uses the model's spatial covariance structure to spread information from the proxy to the rest of the state. And then we come out on the other side with a reconstruction that's spatially complete across the globe, and it's constrained by observations, and we also retain an estimate of the uncertainty. So these are all good things for quantifying pattern effects and their uncertainty, but the bad news you can kind of see here is that for relatively recent reconstructions, which all used data assimilation, end up having what I think at least are non-trivial differences, especially in SST gradients in the tropical Pacific. If you compare them, or the magnitude of cooling in the Southern Ocean, you can see that there are some important differences here, but there is one major feature that they all have in common, and that's, again, this amplified cooling in the North Pacific and the North Atlantic. So we can, again, think that that might end up being important for the LGM feedback. To actually calculate the feedbacks now, we follow the same framework that was used for the historical record pattern effect work. So we start with the global energy balance equation, and then we run simulations in atmosphere models using a prescribed SST and sea ice framework, and we hold the forcing constant across all of the simulations. So we calculate feedbacks just from the changes in TOA radiation divided by the changes in surface temperature, and we're taking differences relative to a baseline control simulation. And the differences in the radiation and the surface temperature are coming only from changing the lower boundary condition for sea surface temperature and sea ice in the model. For our baseline control, we use this data assimilation estimate of the late Holocene. So it's essentially a constraint on the pre-industrial state. And then we run simulations using the SST anomalies from long run MIP, which I showed earlier. And that gives us a 2 times CO2 feedback. And then we prescribe the different reconstructions from the LGM, and that gives us estimates of the LGM feedback. We run this suite of simulations in 5 different models, and that gives us a sense of the uncertainty that comes from different model physics. And then from testing the different LGM patterns, we can sample the uncertainty from different LGM reconstructions. So now what we want to do is compute the pattern effect, and we're going to again follow the same method as was used for the historical record. So we just take the difference between the 2 different feedbacks. And again, these feedbacks are just coming from changing the SST and sea ice boundary conditions in the atmosphere models. And first, I'm going to show the results that are using just one of the LGM SST patterns in all 5 of the AGCMs. You can see that on the left here. And what we end up with from all 5 models is a negative pattern effect overall. And what that means is the 2 times CO2 feedback is more negative than the LGM feedback. And a negative pattern effect implies a decrease in the estimates of ECS. And as a reminder, this is the opposite of the positive pattern effect that was found for the historical record, which increased estimates of ECS. So we're getting the opposite result here in the pattern effect for the LGM. And when we test out these other LGM reconstructions in 2 of the atmosphere models, we find that the negative value of the pattern effect for the most part holds, but we do have quite a bit of spread from uncertainty in the reconstruction. So it's definitely important to take that into account when we're constraining ECS. So ideally now there would be some intuitive explanation for why we're finding a more positive feedback in the LGM compared to 2 times CO2. And what we've done is used radiative kernels to look at which specific feedbacks are responsible for the pattern effect. So now on the right, I'm showing the feedback difference still, but just partitioned into the various component feedbacks. So negative values here are contributing to the overall net negative pattern effect. And perhaps unsurprisingly, the shortwave cloud feedback ends up being a major driver of the negative pattern effect. So I'm going to focus on this feedback for a minute here. Now, I've mentioned a few times now that the SST response to ice sheets is amplified in the North Pacific and the North Atlantic. And if we put these things together with the shortwave cloud feedback as well, we can look at spatial plots of the local TOA radiation change divided by the global mean temperature. So this is just basically a spatial view of the local feedbacks. And I'm showing that just for the shortwave cloud feedback now. It's the middle plots with CO2 on the top and LGM on the bottom. And what you can see here is the LGM has a strong shortwave cloud feedback, strongly positive, right where we expect it in the northern extratropics. And we don't see that so much in the 2 times CO2 SST pattern. There are a few other differences that might jump out and catch your eye, but if you include long wave cloud feedbacks as well and just look at the total cloud feedback, you can see that the main difference that remains is this shortwave cloud effect in the northern extratropics. So we know that that's going to be important for the pattern effect at the LGM. I'll make one final comment on the mechanism. And I don't have time to go into a ton of detail here, but we've run some additional simulations that test whether the feedback difference is truly caused by the SST patterns rather than temperature dependence. And what we did is we removed the changes in global mean temperature and separately computed feedback differences just for the SST patterns. And you can see that the total feedback in the left column is mostly explained by the feedback difference from SST patterns, which is in the middle column. And then the temperature dependence piece is smaller and tends to offset the overall effect. However, it's important to remember that this smaller temperature dependence is just true for this range of climates, and it might not apply, and most likely does not apply when we look at warmer periods. So don't extrapolate this beyond the LGM. Coming back to ECS constraints now, so the final piece of the puzzle. Again, we follow the same method used for the historical record. We're not changing the direct estimates of the LGM feedback at all. So this is just coming from Sherwood et al. 2020, but we're using our simulations to inform the difference in feedbacks. So that's just the delta lambda term. And what we do is we combine the spread that comes from different model physics with the spread that comes from different LGM reconstructions, and that gives us a distribution which we can include in the Sherwood et al. 2020 framework. So on the right now, what I'm showing is first the unchanged LGM evidence likelihood from Sherwood et al. 2020, with one major exception, which is that we did increase the LGM cooling to 6 degrees from 5 degrees, and that's based on some recent studies that have come out and the IPCC reports that gives a higher climate sensitivity. But then we include the pattern effect. And what that does is it brings the tail down and helps narrow the uncertainty on ECS. So again, this is the opposite of what was found for the historical record. Finally, we combine that update to just the LGM evidence with the other lines of evidence in Sherwood et al. 2020, and that gives us a combined PDF. So that's what I'm showing in the box and whisker plots in the bottom here. And we're showing those for both choices of prior from the Sherwood et al. 2020 paper. And what you can see is, with the only difference being accounting for the LGM pattern effect, you get a much narrower uncertainty range and slightly lower values for climate sensitivity just from this one change. So to wrap up now, we found that the feedback from CO2 doubling is more negative than the feedback from LGM forcings. And this difference in feedbacks comes from different SST patterns, and it's mainly driven by the SST response to ice sheets and the cloud feedbacks that follow. And then when we account for the LGM pattern effect, it makes the LGM a stronger constraint on modern day ECS, and that's even after updating the LGM cooling to 6 degrees. So important point here is that as far as we know, this is really the first time that pattern effect work has actually helped us constrain ECS and reduce the uncertainty range rather than blowing it up and going the other direction. I'll just mention that we've got a preprint available on the LGM work at the link here, and we're currently working on Pliocene pattern effects, which I hope to share at AGU later this year. And with that, I'll leave up my conclusions and turn it back to the organizers. Thanks for listening.
Great, thanks, Vince. If anyone has questions, just throw them in the chat. In the meantime, I have one, which is, do you know why, or do you have a sense of why the Annan reconstruction is so different from the other ones?
I do.
Think the yellow one.
Yeah, let me just throw up a reason here. So one reason is they use a multi-model prior. So there's different kind of prior estimates that go in, and they use also annual proxies rather than the seasonal proxies. And because of that, there are also a few models that end up for the LGM having more warming in the Southern Ocean. So the main reason why the pattern effect is smaller for the Annan data is there's a handful of ensemble members that either have really no cooling at all or some warming in the Southern Ocean. So that kind of ends up bringing the pattern effect closer towards 0 or positive values for the Annan ensemble. So there's big differences you can get from different model priors, and that's the main source of the difference here. But there's also different proxies as well and some subtler differences in the methods. So thanks for asking. Good question.
We have another question from Allegra, which says, so the size of the LIS, which is the Laurentide ice sheet, can have significant impacts on the conditions in the North Pacific. Did you try modulating the ice sheet height, Laurentide ice sheet height?
So we didn't actually put the ice sheet in these simulations at all, because that would be part of the forcing component. So things like modulating the ice sheet height, those are all definitely good tests to do, but they would change a different part of the ECS calculation, and that's how big the LGM forcings are. There are some other studies that have done things like that, or put in kind of a flat ice sheet, but still make the ground white to simulate just the albedo effects. For our simulations, we're only changing the SST patterns. So we're just capturing the changes in surface temperature and the feedbacks that follow. So there's no modulating of the ice sheet in our simulations. Thanks for asking.
Oh, we have another one. And yeah, Rob Pinkett says, neat work. Can you explain how you diagnose effective radiative forcing?
Yeah, thanks, Robert. So We didn't do any quantification of the forcing in these simulations. Others have done that work. There's a nice paper by Jung Xu and Chris Polson in 2021 that is where the plots that I showed on effective radiative forcing are actually from that work. So what they did is they took CESM and the atmosphere only configuration and then put in the LGM greenhouse gases, and they put in the LGM ice sheet, but held the rest of the surface temperatures fixed, diagnosed the change in radiative response, and then made an adjustment for surface cooling. But that's from Zhu and Polson 2021. If you're more curious about the effective radiative forcing, I would refer you to that paper.
Yeah, and another clarification from Allegro, which is, so did you plug in the reconstructed SST to a pre-industrial control simulation? Is that an atmosphere only simulation with pre-industrial SSTs to look at the TOA changes?
Reconstructed SST to I'm not sure. So I think if you maybe mean the pre-industrial forcings, yes, the answer to this would be yes. So we plug in the LGM reconstructed SST to get the feedback if you're asking about the forcing, yeah, so there would be you'd keep the forcings at pre-industrial and then, or sorry, keep the SSTs at pre-industrial and change only the forcings and see how the TOA changes. That is indeed the ERF. So that again is in the Zhu and Polson paper, not in the simulations that we did, but yeah, that method is the one used.
I have one more maybe while we wait for other questions. I guess now we can open the floor up, and if people have questions for Guy as well, because Ting had to head off for a sick child, sadly. But I was just going to ask, you also showed this temperature dependence. Mm-hmm. That contribution was increasing between like Cam 4, Cam 5, Cam 6, like pretty, which I thought was kind of interesting. Do you have did you do like a kernel decomposition of that as well, of just the uniform temperature component?
Yeah, I did do that, but I can't remember the results. It was long enough ago, and this is also relevant. I just saw that Nick asked a question. So the positive pattern effect that was in Sherwood et al. Was actually only the temperature dependence component. So what they assumed is essentially something that's equivalent to just the Cam 6 piece. So the size of what was already assumed in Sherwood et al. 2020 for feedback changes for the LGM was just this piece for Cam 6. And we know that Cam 6 has a relatively strong temperature dependence compared to some other models. So this piece, the smaller positive temperature dependence, was already in the Sherwood paper. What they didn't include was the stronger negative pattern effect that comes from the SST pattern. So that was the piece that was missing. When you put the two together, you get obviously a different sign of the delta lambda, and much also it's much larger coming from the SST patterns. To the rest of your question, Andrew, there's a lot of intermodel spread, it seems, from the temperature dependence. So Cam 6 is more positive. Cam 4 is usually small and negative. These results are also consistent with a Block Johnson et al. 2021 paper that looked more at kind of CO2 doubling and quadrupling, but also examined model dependent state dependence. So what we know is there's some uncertainty in the temperature dependence here, and it depends on the model, but it always ends up being smaller than the SST pattern piece for the LGM. Again, it might change for warmer periods, and definitely worth looking at more in the future for things like 8 times CO2. It could be totally the opposite result.
Great. No, that's really interesting.
All right, I'll pull down my slides now. Thanks a lot, guys.
Okay. We got one more comment from Isaac Held here, which says, suppose one is interested in the Southern Hemisphere response to CO2 rather than the global mean. Would this ice age pattern effect change the estimate of the Southern Hemisphere response?
It's a good question. I've only really looked at the values for global mean. I would imagine that having things like long-term ocean circulation and the way the Southern Ocean responds could also be affected, but based on how much spread we have in the different reconstructions and what's going on in the Southern Ocean, it's hard for me to know whether there's a strong signal in the Southern Hemisphere from the ice sheets or if it's just different ocean circulation responses. So I would imagine that there might be an impact on the Southern Hemisphere response, but it's hard for me to comment on that based on the results that we have, just given how much spread there is and what actually happens in the Southern Hemisphere. So yeah, so it's a good question worth thinking on more. Thanks, Isaac.
All right, I think I have to head out. But thanks to all the speakers for a really great set of talks. And thanks everyone for coming and for asking lots of questions in the chat. And we'll see everyone next month.
Thank you.
Thanks, guys.
Bye.